All right.
How are we doing, guys? We are on section 12.2.
Yes, sir.
Chapter 12 still. And again, we just want you to get some broad concepts here. The fact that we're finding surface area, which again is the areas of all the different faces around these shapes. Specifically what we talked about in the last section, what a prism is. A prism is basically if you just put some polygons together, and typically the sides of the prism are rectangles. If you just put those together to build one of these three-dimensional shapes that we've been talking about. And so, and a cylinder, of course, is like a can of beans or soup or whatever. Circular on top with straight down cylinder sides. And so we're going to look at the surface area of those two types of shapes here.
And so I guess, to go right into the prisms here, there's a couple words here. I mean, a prism is to find the surface area of a prism, it's two base areas plus a lateral area. And lateral area, I guess, would just be the parts you could actually see around the front, right?
Right. Lateral means side.
Yeah.
Literally, you can take that from a football perspective of, tossing the ball off to the side or whatever, but the lateral areas or the lateral faces are the side faces.
And then the bases would be the top and the bottom. So if you find the area of the base on the top, the area of the base is on the top and the bottom, and then add it to the area of the faces, then you get your surface area.
Yeah, remember the bases, there's always two of them that are exactly congruent to each other, and they're always parallel to each other.
If you look over at the diagram there, you've got a base on top and a base on bottom in the red there. And then you have your lateral edges, which are your perpendicular edges to the bases. And then your lateral faces would be the two-dimensional shapes that are perpendicular to your bases here.
Right.
Yep. So anyways, we'll look at some examples here in a moment.
So we're looking at continuing with the surface area here, and we want to define the term net. And it's kind of a term that's just thrown around really among teachers. I haven't heard a lot of it out before that. But basically, if you were working for a company and you were in charge of their packaging for their product, whatever product they sell, let's just say that it's a cereal plant, and you had to come up with the box that contained the most volume of cereal for the surface area of it. Well, that box itself, if you take a box, all of us have taken boxes and folded them out flat, or have had a flat box and we had to fold it together. Well, that net is that unfolded box to where it's a flat piece of cardboard that once you folded it together, it would create that box. And so on the right-hand side here, that flattened out, kind of odd-shaped bunch of rectangles put together, if you can kind of go backwards through this to the left, you start folding it up and start creating a box out of that shape then. Well, that flat, unfolded box is called a net. And it just makes it to where it's easier to maybe comprehend the surface area here. We want the surface area of that box on the left. Well, it's the same as all those rectangles inside of that net. And so sometimes it's hard for students to see, you got to do the front and the back. You got to do the right wall and the left wall, and you got to do the bottom and the top. Maybe it's easier for you to flatten it out as a net and find the surface area of all those pieces of that net. But you just need to be able to visualize that, which one goes where, and that they're really the same thing.
Yep.
Okay, so finding the surface area one way or the other here, whether again you take the box put together or you take all the different rectangles and add those all up, one way or the other, it ends up coming out for this box to be 104 square centimeters still, because we're talking about area, and so it's still in square dimensions. And so basically you're going to create a list here and just add up all those different shapes, knowing that they're in pairs essentially. Front and back are the same area, 2 times 5, so 10, twice. Right and left walls are 2 by 6, so that's 12, twice. And then the top and the bottom are 6 by 5 or 30, twice. Add all that up, equals the 104 square centimeters.
All right, now for the surface area of a right prism, there's two formulas depending on what you get here. The formula on top is kind of the general one for most base shapes, triangles or rectangles or trapezoids or parallelogram, but you want to go 2 times the area of the base plus the perimeter times the height of the actual prism itself. Now that's a really tricky thing here, okay? Or if you have like the one on the right here of this pentagon, we got to go back and we got to use our apothem times the perimeter of that pentagon plus the perimeter of the pentagon times the height between bases. So if you look at the key underneath there in yellow, B stands for the area of the base, P stands for perimeter of the base, and h is now the perpendicular height between bases. And so here's where it gets a little bit tricky, because we have a height within the formula for the area of the base, but then we also have the height of the formula between bases, and this is a spot where it can cause a lot of turmoil for kids sometimes. So when we're doing this, just make sure you get that distinction between the height in the formula of the base shape and the height of the actual prism itself. So if looking over here at this pentagonal prism, it's a fun one to say. The height of the actual prism, guys, is 9 feet. Okay, and then we're going to have a apothem here, which is kind of like the height of the pentagon that we're gonna get to here in a moment. Okay, so anyways, let's find the area of this right prism, the surface area of this right prism. So the first thing we need to do is we got to figure out the area of the base. And so what we want to do is we want to pull that triangle out from that picture right there and kind of bring it down there. Now the radius is 6, okay, and that's where that 6 feet comes from on each of those. Those are radiuses that go to that corner. And then A is for the apothem, and then 3.525 feet on each side of that triangle there on the bottom is a 7.05 feet for the side length of the pentagon cut in half. Okay, and so now we want to find A, because we can't find the area of that pentagon without the apothem. So basically, to do that, we're going to use Pythagorean's theorem, okay, and go, c squared minus a squared equals b squared, and so we plug that in right there. Or they do it a squared plus 3.525 squared equals 6 squared. Move things around, square root it, and we get that the apothem is approximately 4.86. Now we just got to go back to the perimeter here, or the formula, and we're going to use that formula of S equals the apothem times the perimeter of the base plus the perimeter of the base times the height between bases. Well, now that I know the apothem, I can figure out the perimeter real easy, because each side length of the pentagon is 7.05. And since the pentagon has 5 sides, I got to go 5 times 7.05, which is going to give me my perimeter of the base. And so that gives me 4.86, which is the apothem, times 35.25, which is the perimeter of the base, plus the perimeter of the base again, which is 35.25, times the height between bases, which is 9 feet. Plug all that into my calculator, and the surface area of this shape is roughly, or approximately, 488.57 feet squared. And it doesn't have the feet squared part on there. It's probably something we need to one of these days go back in there and add it.
But it is in square feet.
But it is in square feet because it's area.
And something I noticed at the top here, the fact that it's a right prism. You guys need to make sure you understand what a right prism is. That means that the lateral faces, the sides around the shape, are perpendicular to the bases. And we kind of said that before, but you just need to make sure you understand what a right prism is. This one, as Mr. Bedella said, is a pentagonal right prism. So we're doing prisms and cylinders. So here's a cylinder example. And a cylinder, again, is like a soup can or chili can or bean can or whatever. And so what you really need to think about when we're talking about this formula is kind of breaking this cylinder apart. And so the 2 pi r squared comes from the fact that we have our two bases are circles. And so on top, if you found the surface area of that base, really this is the same formula as the prism, it's just conformed to circles.
Right.
The circle on top is the base on top is a circle, and so the area of that is pi r squared. But the bottom is the same thing, so there's 2 of those. And so that's why there's 2 times pi r squared. Pi r squared is the area of one of them, and you just double it. The rest of it, if you were to think about that being like a soup can, and I'm sure you've done this before, cut the label on a soup can and taken the label off, you need to think about what shape that label is going to be. So as we take that label off and unfold it, it's going to actually end up being just a rectangle. And so the dimensions of that rectangle is what we need to figure out. And so we end up having the circumference of the circle is really the length of that rectangle. The circumference of the circle comes from 2 pi r. We talked about that before, or diameter times r. But it's 2 pi r ends up being the length of that rectangle, and then the height of your soup can, or the height of your cylinder, is the width of that rectangle. And so that's where the h comes from. So the 2 pi r ends up being the length of the rectangle, the h is the height of the rectangle. We're going to multiply those two together to find the lateral surface area of this cylinder. Okay, so that's how they derive that formula. So looking at this one specifically, let's just plug in. And so in the first part of that formula, 2 pi r squared, the radius it tells us in this diagram is 0.8 inches. So we're going to plug in the 0.8 for r there and square it. And then we're going to have the r again in the 2 pi r, 0.8, and then the height of that cylinder is 2 inches. So we're just plugging in numbers into the formula, calculate that all out, and we get 1.28 pi plus 3.2 pi, and then combine those because they're both just pi's, just like they're both x's or whatever. And we're going to get 4.48 pi square inches. Now again, that's an exact answer in square inches. We could leave it that way if they told us to leave it as an exact answer, or we can approximate it to be about 14.07 square inches. So just depending on how the problem asks you to put that answer, round it off or to leave it in terms of pi. All right. This one is kind of going backwards from that. This one, they're giving you the surface area. They're going to ask you to find the radius of it. And so they give you the height, they give you the surface area. We're going to be solving that same formula just for a different piece of it. Okay? So plugging into that top formula up there, the S is 208 pi from the problem right there. They told us that the surface area is 208 pi square feet. The 2 pi r squared, we don't know what the radius is, and so we can't plug into r. 2 pi r, again, we don't know what the radius is, but we do know the h. We do know the height is 5. And so we've plugged in everything that we can. We need to try to solve that problem algebraically now for r, which is a little bit complicated because there's two of them. One of them squared. This is a little bit complicated. You could do this a couple different ways, but the easiest way would be to look at each one of the two variable representations there, and notice they both have a 2 pi in front of the r's. And so we're going to divide both sides by 2 pi here. It happens to have a pi on the other side, and so it's just going to drop out nice and easy. So the 2 pi, the pi's cancel everywhere. The 2 drops everything in half, and so it makes it 104 on that side. Makes it just r squared, and then 5r. And now you got to remember your algebra here. You got to remember how to solve a quadratic equation here. You got to solve an equation with an r squared in it. Remember, we take everything to one side. So we're going to move that 104 to the other side, subtract it from both sides, and then we have to factor that. So you got to remember how to factor a trinomial here. We need two numbers that multiply to 104 that subtract to 5. And so you can play with some numbers there, but they end up being 13 and 8. And it needs to be a positive 13 because the 5 in the middle is positive. So the larger one has to be positive. Now, remember how to solve an equation like this. You're multiplying two numbers together to give you 0. One of them has to be 0. And so either r plus 13 is 0 or r minus 8 is 0, one of the two. And so that would give us negative 13 as one answer, and 8 is the other answer. Well, we can't have a radius of negative 13. That would mean the circle folds inside of itself or something. Who knows what that means? And so 8 is the only choice here. And so our radius has to be 8 feet for this particular example.
Now, if this problem blew you out of the water, guys, fear not. All right, this is pretty much, I think, the toughest type of problem in the entire book.
Mm-hmm.
I mean, because it has so many things, and
Right.
you just have to pull a lot of algebra out. So, Mr. Scritchfield and I, we're not going to leave you hung out to dry on these. We're gonna work with you guys a little bit and do some examples of these, so you get to see this. I mean, if you can handle this, you can handle anything. I think algebraically in geometry.
Yeah, it's heavy algebra, but that's all it is algebra. And so we'll show you some more examples in class.
Okay.
We'll see you there.